So there's a gap in between the density of states, no? Which we call the forbidden gap or the band gap, no? And this is a gap where there are no real solutions to the density of states equation, meaning that there are no occupiable states in between, right? So talking about the forbidden gap, no, if you solve this equation for different types of materials, right, for different types of molecules like silica, which is an insulator, no, because it's a rock, right? You would find that these have band gaps that are quite large, no. So, for example, for silica, typical rock, you would have 8 electron volts between the valence band edge (EV) and the conduction band edge (EC), right? For diamond, which is just I think it's lang let me ask Google, no? But diamond structure, okay, never mind. So apparently diamond structure is a little more complicated than I thought it would be. But it's a carbon crystal which kind of is reminiscent of our silicon lattice structure, right? Because our silicon lattice structure, each silicon atom is bonded to 4 other silicon atoms, right? So then for carbon, it would be the same, right? Each carbon atom would have to be bonded to 4 other carbon atoms in its lattice structure kasi it also has 4 valence electrons. No? The thing is, for diamond, this structure allows for much tighter bonds between the electron and its host atom, no? And it makes it so that it takes around 5 electron volts of energy. Takes around 5 electron volts of energy to actually break that binding energy and separate the electron from its hole, meaning that the electron becomes a carrier, the hole becomes a carrier. No, so insulators are extremely hard to break like this. Semiconductors, on the other hand, have band gaps on the order of around 1.12 electron volts. No, and metals have no band gap whatsoever, meaning that their conduction band and valence band overlap, and that's why they can conduct electricity very, very well, even at 0 degrees of temperature. No, because they don't have any band gap whatsoever to skip, no, from the contribution of temperature. No, you'll also find here over in this slide that there's about at 300 degrees Kelvin, no, heat zaps electrons, no, through this gap around 26 milli electron volts on average, no. So that's our 0.026, no. Now, what is the intuition behind calling this zapping electrons upwards? The thing is, no, this 26 milli electron volts is this one, no? So it's K times D, no? K is Boltzmann's constant. And if you've not very much encountered Boltzmann's constant before, Boltzmann's constant essentially says that in an ideal gas, no? In an ideal gas, depending on the temperature, no? So that's why per Kelvin to, no? Depending on the temperature in Kelvin, each particle receives that amount of energy from heat on average, no? So if you had some particle here, it would receive this much per unit of Kelvin, no? Energy from just that temperature, no? So if you multiply by kT, you get that each electron receives about 0.026 millivolts, electron volts, no, not millivolts, 0.026 electron volts of heat or of heat energy on average, no? And the reason that this appears in the Fermi function is why? The Fermi function that says that like this, the Fermi function is how likely you are to find an electron occupying a state, no? And the thing that influences electrons to be a carrier, no? Or to be here, for example, no? The thing that influences electrons to be here in a semiconductor is heat, right? Because you need heat to promote electrons from here to up there, right? That's why it makes sense that the Fermi function is shaped depending on the temperature, no? Now, likewise, if we set the temperature to 0 and calculate this equation, we would find something like 1 over 1 plus e to the e minus ef over 0, no? Which, okay, let's do some, calculus, no? So we're gonna take the limit instead, no? As this thing approaches 0 from the positive side, which means it's going to be, this thing is going to be approaching positive infinity. Approaching positive infinity, and then, okay, if that thing approaches positive infinity, this entire thing at the bottom would approach positive infinity by itself, which means na it's going to be either 0, no, kapag E is greater than EF, no? So it depends on the sign of this thing kasi. So E minus EF over 0 from the positive side, no? So let's just redraw it here, no? E to the minus, E minus EF over KT as KT approaches 0, right? If KT approaches 0, then it depends on on the sign of this, no? Kung negative to, then it's going to approach negative infinity, right? Kung positive to, then it's going to approach positive infinity, right? So I hope that one makes sense. So then, what happens here is, kapag positive to, meaning that E is greater than EF, no? Then it implies na positive infinity siya, meaning that our limit is 0, right? So it goes to 0. Tapos, at E less than EF, no? Then that means negative yung nasa taas over 0 plus, no? Approaching 0 from the positive side. Then this would be negative infinity, right? Meaning that this would be 1 plus e to the minus infinity, which is 0, no? So it's 1 over 1 equals 1, no? And we get this part, right? So I just showed you guys how we got this flat band, no? But as t approaches 0, what I want you guys to notice is this one is flat 0, and this other one is a flat 1, right? So then at 0 degrees Kelvin, or at 0 Kelvin, rather, it's not degrees, it is impossible to find electrons on the conduction band, and all of them would be in the valence band, no? In other words, also, there are no holes in the valence band. So then, at 0 Kelvin, the silicon cannot conduct electricity, no, making it not a metal, right? All right. So, any questions with that? That is what that is where we left off from last lecture. All right, sige. So, if there are no questions, I'll be proceeding ahead to the next slide, no? So, since the Fermi function, no, f of E, tells us the probability that an electron is occupying a specific energy level, and we know the density of states, no? We know how many states there are in an energy level, no? So, this is GC and GV. Then we can derive the number of electrons and the number of holes per energy level, right? Because you just need to multiply a probability that an electron is in this energy level times the number of states in that energy level, no? Likewise, if we do 1 minus F, no? 1 minus the Fermi probability, then you get the probability that an electron is not in a state, no? That a state is empty, rather, no? So if we multiply 1 minus F, no, to the density of states in the valence band, then we get the number of holes in the valence band, no? Now, something to note here is that the number of electrons maxes out, no, somewhere after, like somewhere a little after EC, no? It doesn't actually, the number of electrons does not actually grow exponentially, no? Or does not actually grow steadily, but rather it maxes out and then it falls off, no? Unlike the density of states, no? Likewise, the number of holes maxes out a little after EV, not exactly at EV, no? It maxes out a little after EV, and then it falls off, no? And we will get how to interpret this in the next lecture, I'm pretty sure, no? But essentially, no, what we can take away from this, what like an intuition that we can probably gather, no, from this type of behavior is that electrons tend to want to stay close to the conduction band edge, and holes tend to want to stay close to the valence band edge, no? It's just that they're not so easily allowed to be there. Bakit? Kasi there's much less states at the edge, right? There's actually no states exactly at the edge, no? Now, also, another thing is that since ito yung electrons per energy, we can recognize na ano yung mangyayari kapag in-integrate ko to, no? So, kung ito yung electrons at this energy level, no? Then if I take the area under this, then it should give me the total number of electrons in the material per cm squared, no? Bakit siya per cm squared? The density of states has units in terms of per cm cube, no? Hindi pala cm, cm squared, no? Density of states natin, ang units nito is per cm cube, no? So then when we multiply it to a Fermi probability, which is unitless, we also get the number of electrons per cm cube, no? So then when we integrate this thing, when we integrate this carrier density graph na meron tayo, no? According to the energy band diagram, we integrate that from here to positive infinity, no? Ito pala yan dito sa taas. Then what we get would be, what we should get, rather, is 10 to the 10, no? For 300K silicon. Kung 300K, 300 degrees Kelvin yung ginamit natin for making this Fermi probability graph, no? Remember, Fermi probability depends on the, it's e to the E minus EF over KT, right? So, yan siya. Likewise, no? If we integrate this one from here to negative infinity, we get the total number of holes, no? Which should be about 10 to the 10 as well. All right. So, now that we've, again, talked about that one, let's talk about doping, no? So, do you guys remember what doping is? Who knows, who remembers what doping is? Please give me a thumbs up. All right, great. So seems everyone remembers naman what doping is, no? Now, since the carrier concentrations essentially, right, depend on the position of the Fermi energy level, no? Ito, kasi, right, if we shift the Fermi probability up or down, no? Then tataas yung probability dito, right? Tataas yung probability that states in the conduction band, no? Yung density of states natin, right? Multiply it with that, tataas yung probability na occupied yung states na yun, thus increasing the number of electrons right here, no? And if we integrate that, we get something that's greater than 10 to the 10, no? Which agrees with what we know. Kapag nag-dope tayo, no? When we dope the silicon, we introduce more carriers, no? One way or the other, right? So then, introducing the concept of doping to our energy band diagrams, we can relate the shifting of the Fermi energy level, no? So we can say that doping effectively moves the Fermi energy level up or down, depending on what you dope the material with, no? And we have this equation to do so, no? Rather, we have this equation to tell how much the number of carriers changes with respect to the Fermi, the shift in the Fermi energy level. Now, vice versa as well, no? Kasi we have the equations, no? We have the earlier equations. We have ND minus NA over 2 plus square root of ND minus NA over 2 squared plus NI squared, no? Square root over all of these, no? Ito yung N, right? So then, since we know what N is, we can just rearrange this equation to find the amount of shift in the Fermi energy level, no? Now, what is EI in this case? EI in this case is the intrinsic Fermi level, no? It's where the Fermi level was when the silicon was still intrinsic, no? So that is, so this shift, no? The number of total carriers is exponentially proportional to this shift in the Fermi energy level, no? So that's what we, so that's the intuition, no, that we would like to build here, no? The closer EF is to, say, the conduction band, no, the more electrons you will find in the conduction band. Vice versa, if the Fermi energy level was down here, right, and it was closer to the valence band, onti yung electrons natin, dadami yung holes, no? Bakit onti yung electrons? Because if you shift the probability, no? If you shift the probability down here, right? Then, bumaba relatively yung probability na may electron dun sa states natin sa conduction band, right? So it's like the carriers want to be close to the Fermi energy level, no? Which they do want to be, right? That's what we interpret the Fermi level being, no? So, for another concept, no? We don't want to dope too many atoms, no, into our semiconductor material, no? Why is that? It changes the properties permanently, no? Well, I may be lying when I say we don't want to do that. We do want to do that sometimes if we want to make essentially a metal, no, dun sa silicon sheet na ginagamit natin para mag-fabricate ng electronics, no? Kaso, there are better ways to do so, like using copper, no? Kasi, if we put too many dopants into a semiconductor, it turns essentially into very close to a metal, no? And the equations that we've talked about, like these ones, no? Like itong, especially itong KTLN, um, N over Ni, no? So the ratio of the current number of electrons over the intrinsic concentration, which is 10 to the 10, no? This equation would not hold kapag degenerate na yung material, no? So we do always have to take into account kung kailan magiging degenerate yung material. Now, TRA's book, no, defines degeneracy as if the the Fermi energy level gets closer to the band edges, no? So this is conduction band edge, right? And this is valence band edge kasi mas mababa yung valence band edge. If it's 3 kT within the distance, no? The distance between your Fermi energy level and the conduction band edge is within 3 kT already. It's that close. Then, degenerate na ang tawag mo sa semiconductor. What's with the degenerate semiconductor? You have way too many carrier electrons that you start behaving like a metal, no? Which means that the equations that we've always had for the equations that we've had so far, no? These things have an assumption na meron tayong thermal generation of carriers. Kapag masyado nang marami yung electrons, no? it starts dominating. No, the number of carriers that are there to begin with starts dominating the number of carriers that were that aren't there, no? That aren't there yet, no? That need to be created with thermal energy, which is a property of semiconductors that we like, no? So at this point, hindi na valid yung mga equations natin, which is why we don't like degeneracy, no? And what's interesting about this is, since precise yung definition niya, no? And alam natin, right? Alam natin kung gaano kalaki yung band gap ng silicon. Who remembers how large the band gap of silicon is? It's like with this, no? Of course, it's like a little over 1 volt. It's 1.12, right? Nice, correct. So it's 1.12 electron volts, right? So then, we can calculate this, right? So ano ang 3 kT? It's 3 times 0.026 electron volts, right? Which is around 0.026, 6, 12, 18, 6 plus 18, that's around 0.78, 0.078. Actually, I did the math down here already. So, kaso, sige, let's do it in formalities, no? So, 3 kT is around 0.078 electron volts, right? So then, this specific energy would be half of the band gap, no? 1.12 EV over 2, no? So that's this thing, right? Half of the band gap minus 3 kT, right? So minus 3 kT, it would be this thing, no? So minus 3 kT would be equal to about 0.0482 daw, sabi nung gawa ko, no? So ito no? Ito yung distance na to, no? So then, if we apply that to become equal to EF minus EI, no? Or rather, ginawa kong inequality, no? It must be that to consider a material degenerate, EF minus EI must be greater than this distance, right? Makes sense naman. So then, if you solve that, you get an ND, no? And we find that ND has to be greater than 1.12 times 10 to the 18, no? Now, the general rule of thumb is to consider any doping concentration above 10 to the 18 degenerate. Now, dito sa solution na to, meron akong assumption. Can someone point out kung ano yung assumption ko for this solution? Ano yung original equation na ginamit ko dito? This is EF minus EI equals KT ln watt over watt, no? We have something over Ni dito sa equation na to. N, right? Eh ano nilagay ko dito? ND, no? So ang assumption natin dito is ND is high enough to drown out the intrinsic carrier concentration. And it is also enough to drown out the dopant concentration. And this is a sound assumption to make for deriving the degenerate concentration. Bakit? Kasi sobrang dami na nga nila na degenerate sila. Ano ba yung intrinsic carrier concentration at room temperature? That's 300, that's the 300K. At room temperature, that's 10 to the 10. 10 to the 18 is not even close to 10 to the 10. It's way more than 3 apart. It's 8 apart, right? So it's 8 degrees of magnitude apart. That's why we don't, that's why this is a fine assumption to make for this one, no? Conversely, kapag ginawa natin yung calculation pababa, we're going to get the same thing, no? Na greater than 1.12 times 10 to the 18 would render it degenerate with holes, no? Masyado na maraming holes that the traveling of the holes renders it similar to a metal. By the way, no? When we do, sige, may lecture summary dito. So I'll put it in this slide before I go talking about these other things. So for example, no, meron akong metal contacts, no? So this is copper metal contact na pumapasok sa isang semiconductor, no? And in typical analysis, actually, you can assume that this is an infinite source of electrons, but it is also an infinite source of holes, no? So that's a particularly interesting thing about metals is that it's so full of electrons that it has a lot of space to take in electrons as well, no? Which means it can provide holes for your semiconductor. So, okay, that's lecture summary, cheat sheet, no? So these are things that are provided for you guys kapag nagre-review kayo. No? So I'm not going to, repeat everything. All right, any questions about this first part? All right. So kung wala naman, I will give the attendance Google form for now, and then let's take a 5-minute break. By the way, tanong lang guys. Kapag na-disconnect kayo dun sa Zoom call, tapos tapos saka kayo bumalik, um, nawawala ba yung link ng Google Form? Nawawala yung link ng Google Form. Okay, so in this case, um, okay, what I advise you guys to do is to try to accomplish the Google Form as soon as it is sent into here. And also, no, ang gagawin ko ngayon is gagawa ko ng text channel dun sa Discord natin named attendance, and I will be sending the attendance Google Form over there. Kasi, ang meron dito sa mga Google Form na to, it takes the timestamp, right? So, what I will be doing to know that you guys um, are attending, no, when you do the Google Form is to have, titingnan ko na lang yung timestamp, no, kung kailan nyo siya in-accomplish. And to be honest, I could also always delete the link in the attendance channel, no? I'm not particularly strict naman. Alright, sige. So let's move on to carrier action, right? Which is the actual lecture for today. So when we say carrier action, it is what our carriers do, no? Or what what things everywhere do to create carriers, no? Essentially is what happens, right? And ano ulit yung carriers natin? We have the electrons, no? We have the electrons and we have the holes, no? So those what the electrons, what the holes do, that is what carrier action is, no? All right. So first, let's talk about drift, no? The thing is, no, we know from Physics 72, no, that an electric field applied to a charged particle causes a force proportional to the charge in the direction of the electric field, no? So we know that from Physics 72, right? And the same happens for electrons, and the same happens for holes, right? So holes, no? Let's call it H, no? Tawagin natin sa pangalang H. The hole would also be influenced by the electric field to go in this direction with the force F, no? Kaso, mas mababa yung force kay hole, no? For reasons that we're gonna talk about. Anyway, no? We apply a force to holes in the opposite direction as we apply a force to the electrons, no? Because electrons are negatively charged, they are pushed towards the source of the electric field. Holes are pushed away from the source of the electric field, no? So um that is the elementary physics of it, right? Makes sense naman. Kaso in a lattice, no? It's like playing pinball. There's a lot of things to bump into. For example, we have the electron right here, no? It's exposed to an electric field going to the left. So it's encouraged to go this way. Kaso, because of temperature, no, the way that it goes to the left is kind of wiggly, no, because it vibrates. That's what temperature is. No, it's kind of like vibration, right? So it cannot go in a straight line. Starts going in all sorts of directions. And to make things worse, it's like pinball, no, or pachinko, in like Japanese culture. Um, I feel like pachinko is a better thing for it kasi mas uniform yung mga pins doon. Kaso, the electron hits silicon atoms every time, no? So what happens is that the electron starts getting faster, getting faster, getting faster, and then it bumps into a silicon atom, no? And then it gets slower again. And then it starts getting faster, and then faster, and then faster, and it bumps again, no? So it's like a car stuck in traffic, no? Is what's happening to the electron. And that's not the only thing, no? Dopant scattering also happens. It's not just silicon, right? In our semiconductor lattice, no? We have around, 10 to the 15 in a p-type semiconductor. By the way, what's a p-type semiconductor? Anong element yung idodope natin para maging p-type yung semiconductor? Boron, yes, exactly. Because boron, no? Boron B has 3 valence electrons. So it introduces one hole, right? And if you have a lot of holes, that's a lot of positive charges moving around. That's why we call it p-type, no? So anyway, no? This semiconductor is actually n-type because it's phosphorus that's here, no? That's what the P means. Anyway, when you have a semiconductor that is doped, no? Yung dopants na yun, they actually mess with the electron a lot more than the silicons. Bakit? Because these are charged, right? this is a phosphorus atom that has lost one of its electrons, meaning there's a net positive charge, right? Bakit? Kasi it has 5, 14, 15. It has 15 protons, but just 14 electrons now, right? So there's a net positive charge, no? Anong ginagawa ng positive charge kay electron? Even if the electron was going to narrowly miss this, it's going to bump into it because it's going to curve a little bit, no? That's why dopant scattering is actually worse than the typical silicon lattice scattering, no? And these are our two types of scattering. So lattice scattering against silicon, dopant scattering against dopants, no? So this movement is also this movement is all called scattering, no? The bumping into each other, collisions in the quantum realm, you call that scattering, no? As an extra trivia, the reason why the sky is blue is called Rayleigh scattering, no? Because the light scatters because it hits the particles in the sky, no? So tatama yung lights, ganun siya. Yung blue yung napupunta sa yung blue yung nasa scatter. Kaya blue yung nakikita natin and everything else is not scattered, no? So that's what happens in the night sky. And the night sky and the day sky, no? Of course, black lang siya kapag night. Anyway, back to this, no? So the electron, right? Accelerates, 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 bumps, accelerates, 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 bumps, no? And like a car is stuck in traffic, there is a net velocity that takes you like 3 hours to get to class, no? And also takes me 3 hours to get to my own lecture. This is why this is why we're partially online class. Anyway, it's called effective velocity, no? Because you are accelerate, you bump into something, you stop accelerate, you lose all of that effort, and then you start accelerating again, no? So it has an effective constant velocity when it moves around, no? Electrons and holes alike, no? So we have this effective constant drift velocity, VD, that we get for applying an electric field, no, to the carriers, no? So then, if we assume, no, na totoo nga, okay, may constant velocity na na-apply dun sa carriers, no, then we could write the total carriers, no, passing through a plane, no. So look at this figure, no. We could count the total number of holes, no, passing through a plane by counting the velocity, no. So all carriers, no, all holes, the number of holes, no, that will pass through an area A at any given moment, no, are at some speed, no, per second to, no. So for example, per second to, ito yun, no, because it's the carrier concentration per centimeter cube times velocity, no, which is centimeters per second, for example, times centimeter squared, no. This all adds up to 1/second, right? So this is the number of holes per second passing through this cross-sectional area, right? And same happens, no? The exercise is left to the reader for, for this one, but the same thing happens for electrons, right? So now that we know how many carriers passes through, all we need to do really, no, is to multiply that with the charge, right? Magiging ganito yun, no? So you multiply this with Q to get the total amount of charge passing through this area per second. And you multiply also this with Q to get the total amount of charge passing through this area per second, no? So this is negative Q. It's also negative Q. No, mamaya pa siya hindi magiging negative Q. Sorry about that. Maybe I'll fix that typo as well. So negative dapat yan. Kasi negative Q ang electrons, right? But really, all we did was to multiply Q, no? To get the amount of charge passing through a cross-sectional area at any given point in time, no? Which is the definition of current. Now, if we remove the area part, no? Because we sometimes don't know the area, we get a current density. no? So that's a concept from Physics 72, I'm pretty sure. Tanggalin mo lang yung area, no? And Q is the electron charge, which apparently in the previous slides I wrote this as 9, so I'm sorry about that. This is 1.602 times 10 to the minus 19. All right. Next, we talk about something, no, that we call mobility. Kasi 'di ba? Okay. The electric field causes carriers to move around in the lattice, right? So meron kang electric field, this thing starts going, no? Depending on the strength of the electric field, this thing starts accelerating faster, right? That's what's happening, no? So then, the effective drift velocity should also get faster. VDN pala to, no? The effective drift velocity should also get faster with respect to the electric field, no? And the experimental physicists, they measured this and found na ito yung graph, no? It's actually quite linear. Na yung drift velocity ng mga electrons actually corresponds in a linear fashion to the electric field strength down here, no? So then, we could build an equation of the relationship like this, no? So the velocity is equal to some relation, no, some linear constant times the current electric field, no? Wala tayong plus C dito. Bakit? Kasi at zero electric field, of course, zero yung drift velocity, no? Anyway, so meron tayong constant of proportionality, so to speak, which is the mu, no? This is the mobility. So, ayan, no? And since it's the constant of proportionality of a linear thing, let's just rise over run, right? So ito yun. But notice here, no? The velocity saturates. The velocity saturates at some point, no? Masyadong mataas yung velocity. Even if you increase the electric field, hindi na bibilis yung carriers mo. Why? Because it's bumping into too many silicon. No, masyado ng like it doesn't matter how fast you get, you're just going to start bumping into things faster, no? So that's a problem, no? That's it saturates. But it's not a problem for us, no? Bakit? Because we don't usually get to this type of high electric fields, no? That's a problem for it's a specific design problem for specific circuits, but not for our purposes, no? So for all intents and purposes, the mobility stays constant. Okay, so a task for you guys is imagine kung ano yung graph ni mobility versus the electric field. Does anyone have any idea how we're going to make a graph of the mobility? Slope siya, di ba? So then, all we have to do is to take the derivative, right? And the derivative of this thing is going to be something like this, no? The mobility dies once the velocity saturates, no? But it's fairly constant over here, no? Yun namang naman yung kita natin about the velocity. All right. Typical values for the effective mobility is this one, no? So mu n at 300K silicon is around 1350 cm squared per volt second. Remember the units, guys, kasi the units are fairly important for you guys to sanity check your calculations, no? It's very important, no? Kasi if you don't remember the exact equations, tas may tinatanong sa'yo, you will be able to derive exactly what you need by looking at the units. Like for example, no? Mobility is cm squared per volt second, right? If we multiply that to an electric field, which is volts per centimeter, no? You can see that there, no? Volts per centimeter. Usually it's volts per meter in physics 72, but centimeter ang gamit natin dito because that's a more realistic unit, no? For this type of very small scale things, right? Magka-cancel yung 2 centimeter. You're left with cm per second, which, voila, it's your velocity, right? Also, no? Um, sige, velocity, um, mm, velocity PQ, right? So, velocity times the number of holes times Q, no, times area, no? So, let's try to analyze the units here. cm squared, cm per second, per cm cube, no? Per cm cube yung P natin, di ba? Because there's the number of holes. And charges in coulombs, right? Cancel yung lahat ng cm natin, you get coulombs per second. Ano ang coulombs per second? That's an ampere, no? Which is your current, right? Okay. Right. So, next, let's talk about how velocity changes, no? So, as before, I said na we just take the derivative of this velocity graph and we get the graph of the mobility, no, which is down here, right? It dies off at around the saturation velocity, right? Also, hindi pala, no? Okay, never mind, no? This is not versus E, this is versus impurity concentration. What is meant by this graph, no? Okay. What does it mean when it says total impurity concentration? No? What would be an equation that we have to represent the total impurity concentration? Impurity meaning dopants, right? Total dopant concentration would be if you add Na and Nd, right? So if you add Na and Nd, you would get the total impurity concentration. Now, this graph says, no? These graphs are just here for, ano, no? For demonstration purposes, no? So it's not something that you have to memorize, of course, because it's a graph, no? It's probably going to be given if you're ever going to use it. But the mobilities get reduced as you increase the number of dopants. Why? Because of dopant scattering, di ba? Nasabi na natin, if there's more dopants to scatter with, then there's, there's a higher chance of you losing your velocity. So your effective mobility gets decreased, no? Likewise, against increasing temperature, bumababa din yung mobility natin, no? So shown here for electron mobility, no? Kita mo, pababa siya ng pababa doon, no? And you can also see, no? Na pababa din siya ng pababa against the number of dopants, no? Here shown as the number of donors, right? So it actually is kind of a trade-off, no? Kasi intuitively, kung gusto mong bawasan yung resistance, right? Kung gusto mong bawasan yung resistance nung block of silicon mo, gusto mong damihan yung electrons, right? But apparently, if you increase the number of electrons, bababa yung mobility, ay yung dopants, no? Bababa yung mobility. So which one actually wins in the end? Right. So now let's talk about resistivity, no? So there's a current, no, due to drift, which we now know because kanina Qn velocity times A yung equation natin. We now have Qn mu n A, Qp mu Pa times the electric field, no? To calculate our total currents, no? So, since the electric field is calculated as volts over length, no? Remember, its units is volts per centimeter, ang unit ng electric field natin. Then, after some derivation, no? So, I and drift is equal to volt over length, no? So, we just turned electric field into V over L here, no? So, ito yan. Tapos, alam natin na a current is volts over resistance, right? Then, we could place it in this manner, no? Na this equation is equal to V over R, no? So, in the end, ang mangyayari, magka-cancel out si V and we're left with this equation, no? Tapos, if we apply the equation rho L over A, no? Which is the definition of resistivity, we get this equation, no? So, the resistivity is 1 over Q times the total of the number of holes times mobility, hole mobility, plus the number of total electrons times the electron mobility, no? So all you really need to remember from this concept, no? And it's actually quite a favorite concept to give problems on, no? So if anything if there's anything you would like to take away from this lecture, it would be that this is the resistivity, no? And this would get you far, essentially, no? All right. And, it's actually quite an elegant equation. Kasi, dindikit mo si P with a mu P, dindikit mo si N with a mu N, and you multiply all of it with charge, no? This is also a reason why I told you guys to, like, isa puso nyo yung units. Kasi, to, ang P, no? Ang P, right? Ang P is per cm cube, right? Sa concentration. Ang mu P is cm squared per volt second, right? That's what we told about earlier, right? So then, makukuha mo dito is cancel to, no? So C over cm times volt second, no? Now, pretty sure some students have had the idea to try to derive the units of an ohm, no? But anyway, here's some extra trivia. C over volt second is actually ohms, no? Bakit? Kasi C over second is amperes, right? C over second is amperes. So amperes per volt is ohm, no? So this becomes ohm. Baliktad, no? So this becomes 1 over ohm cm, no? Which is exactly what we want naman, no? Kasi 1 over ohm cm is ohm cm, which is the units of resistivity, no? So the unit of resistivity is an ohm cm. If it doesn't shape out to be an ohm cm, then you probably got something wrong. Most of the time, mistake is hindi nilagay yung Q, hindi naging coulomb, so hindi naging ampere, no? So yan. All right. Sige. Any questions so far? All right. Sige. So if there are no questions, I'll go ahead to boom, diffusion, no? So this is cool. Kasi it's intuitive, no? May dumaang kotse, nagbelt siya ng smoke, no? Ginawa ng smoke, pumasok sa bahay mo. Hanggang CR pasok yung amoy ng smoke, no? Bakit? Because of diffusion. Because of because the smoke belcher, when the smoke comes out of its anong tambucho? Exhaust, no? When the smoke comes out of the exhaust, it's very concentrated. And the tendency of very concentrated things is that it wants to disperse, no? It wants to spread out, no? And it's a physical law, no? So the same thing happens for electrons and holes, no? For our carriers, it also happens. They don't like being close to each other. Why? Because they're the same charged particles, right? It also makes sense. If I have electron here and electron there, they're both negatively charged. Yeah, they're both negatively charged, so they go away from each other, right? That's what's happening. So, likewise, if we have a changing carrier concentration over a silicon block, no? So let's assume na one-dimensional yung silicon block, wire lang siya, no? Tapos mas maraming electrons dun sa gitna. By the way, this actually does happen, no? Meron tayong physical example just in the next slide. Then, they're going to disperse that way, no? And since gumagalaw yung carriers, magkakaroon ng current, no? So, okay. I'm going to divide this into two halves. Okay. So, if the carriers were N dito sa graph na to, ano yung direction ng current for this half, no? So, for half number 1, ano yung direction ng current dito? If this were electrons. So then, right, the electrons would be moving that way. Kasi they're diffusing away from each other. If the electrons are moving that way, and electrons are negatively charged, then that means that there's a net negative charge moving that way. Meaning, positive current is in that direction, right? On the other hand, no, positive current will be in this direction for here. Kasi pag ganun yung movement ng electrons, right? So that's something to note about diffusion. No? Depends on the charge of your carrier. Right? On the other hand, kung holes to, no? Kung holes to, then the holes will be moving that way. And since holes are positively charged, then the charge is going that way. Right? Because current is the direction of movement of positive charges. Right? Holes would also be going this way. So then, current would be this way. No? If it were holes. Right? All right. Now, we represent this diffusion movement by saying that the current density is proportional to the derivative. No? And the reason why I asked you guys kung alam niyo yung gradient is kasi actually it's not just the derivative, it's the gradient, no, of the concentration. Because, you know, we would like to solve for the case kapag na hindi na one-dimensional yung semiconductor natin, no? So in general, this is actually the gradient, no, of the concentration. Anyway, we have here the diffusion coefficient, no? So we multiply the diffusion coefficient with the change in density, no? So the change in density essentially is pag ganun, di ba? So okay, let's examine, no? Bakit ganyan yung sign niya. So let's assume, for example, that this is hole, no? Holes tong nagdi-diffuse dito. So kung holes to, then this slope would be positive, right? And according to the positive slope, the holes would move in the negative x direction. So then, negative dp over dp over dx, no? So dp over dx ang direction of movement, no? Times q dp, and you have the diffusion. You have the diffusion current, no? Likewise, okay, let's assume this time na electrons, right? So kung electrons, all right, so positive yung slope, right? Positive yung slope. So then, positive yung slope, kaso electrons are moving to negative x, right? So the electron movement direction is negative dn over dx. At least is proportional to that. And net electron movement is actually dn. Tapos, i-multiply natin siya with the charge of an electron, no? Which is negative Q, right? So magka-cancel yung negative, no? So we have here, no? Magka-cancel yung dalawang negative, you get positive, no? Which is exactly this equation right here, no? Now, how do we get the diffusion coefficients? You'll see later on actually how we got these equations, but for now, let's just thank Einstein. Thank you, Einstein, because these are the Einstein relationship, no? The electron mobility is related to kT over Q, no, which is 0.026, but in volts this time, not electron volts, is proportional to dN over mu n, no? So really, this equation would be all would tend to be used like this, no? So dN equals mu n times 0.026 volts, no? All right, so I hope that makes sense, no? That this one is just a magic equation na binigay sa atin ni Einstein, and we're going to make the most of it by analyzing the units, no? So this is cm squared per volt second times volt, meaning that the diffusion coefficient is actually cm squared per second, no? Now, this is left as an exercise to the reader, but apply that to this, no? And you will see na current density yung lalabas, no? So ampere per cm squared. You might ask, sir, ano yung units ng dN over dx? Well, this is over cm cube yung n, di ba? Over cm. This is 1 over cm to the 4. All right. So that's it about elementaries of diffusion. And diffusion is actually one of the things about semiconductors that you can observe, no? Like that you can directly observe. I'm not sure if may lab class pa na equivalent ang 131, but it used to be na merong lab class na kasama yung 41, which is this subject. And you are, in the lab session following this lecture, you're usually given a block of silicon, no? A square block of silicon. And you're gonna have to scratch it kasi ang nangyayari is may silicon, no? May silicon block ka. Tapos nagkakaroon ng thin layer of silicon dioxide, no? Silicon oxide dun sa taas kasi you usually shield it from oxygen, but because oxygen is in the atmosphere, kakaroon ng thin layer, so you scratch that away. And then when you scratch that away, you're going to put in the red terminal of your multimeter, no? And the prerequisite is i-heat mo muna yung red terminal, no? Paano mo i-heat yung red terminal? Usually sa lab ang ginagawa sa kanya is ilalagay mo siya sa soldering iron, no, para uminit, or lighter, no, essentially. But because this changes far, remember, heat turns non-carriers into carriers, right? In the energy band diagram, pag may electron ka dito, tapos binigyan mo siya ng heat, di ba napupunta siya sa conduction band? So, kapag nag-introduce ka ng heat dun sa isang section ng silicon, tataas yung carrier concentration, no? So now, if you put that into the square block of silicon, no, usually yung two corners yung ginagawa mo, no? You get a distribution of carriers, no? So the hot point probe experiment allows you to determine kung sino yung majority carrier, no? So ito, for example, holes, no? Kapag hole yung majority carrier, okay. Can anyone tell me what type of semiconductor this one is? Holes. Holes yung carrier mo. Which means this is p-type, right? This is n-type. Okay. So kapag holes yung majority carrier mo, then the hot probe will make a lot of holes here. So then magdi-diffuse yung holes pa ganon. So anong direction yung current? Pa ganon, kasi holes are positively charged. And current is the direction of positive charge, right? So then, if you complete the circuit, sabihin ng ammeter mo, there's a current going that way, no? And that's how you tell that it's a p-type. Likewise, no? If it's an n-type, no? If it's an n-type semiconductor, dadami yung electrons because of the hot probe, right? So then, electron diffusion will go this way. So saang direction yung current? It will go opposite of the electrons. Kasi electrons are negatively charged, right? So then, this current is going that way, no? So, sorry. This current is going that way, meaning it's going to ride up your probe and go through your ammeter, no? To short circuit around. And sasabihin ng ammeter mo, type po to, is positive 0.1, no? And that's how you're able to tell between a p-type and an n-type semiconductor, no? So this is one macro scale experiment that depends on this all of these quantum equations and allows us to actually identify something that we can experiment with in real life, no? Ayan. All right. So any questions about diffusion? All right, sige. So if there are no questions about diffusion, let's go on to the last part of today's lesson, RG. No? So RG, when we say RG, no, we mean recombination and generation. No? So carriers, as we know from the hot point probe experiment, right? They're generated by heat. No? So we can represent that in this diagram, no? Dun sa energy band diagram. You have an electron, no? So nagsimula ka na may electron, and it gets zapped with heat. So then it jumps, no? So ito na yung nangyari after the jump, right? Pumasok yung heat dun sa electron, it jumps up in the energy to the conduction band, no? Where it jumped up, may iwang hole, no? So then you call this direct thermal generation, no? You generate a pair of carriers, one hole, one electron, directly from thermal, no? Direct kasi it jumped directly from the valence band to the conduction band, no? Next, we also have direct thermal recombination, no? So remember in Discord I asked, no, what happens when an electron and hole meet, no? And some people actually answered yung I think this one, and so in a sense this is actually quite correct, no? So direct thermal recombination is when an electron and a hole meet and the electron falls into the hole. But to fall into the hole, it actually has to lose energy. So when it falls into the hole, it actually releases a photon, no? It releases a photon para makapasok siya dun sa, para malaglag siya dun sa hole, no? And essentially, no, just like a particle and just like matter and antimatter, when they meet, they annihilate, no? So you lose both the carrier electron and the carrier hole, no? In this case. So from that, no, and generation is the process of creation of pairs. Recombination is the process of annihilation of pairs of carriers, no? Right. So RG centers. So in silicon lattices, no? So guide your eyes to down here, no? In silicon lattices, lattice imperfections exist. No, there are like things that are missing. There are things that are extra. There are things that are not supposed to be there. Like for example, copper, no, because you'll never find ultra pure silicon. No, ultra pure silicon is still not 100% just silicon. But so anyway, lattice imperfections exist, and these provide extra energy levels. No, like for example here, electrons find it less easy to be in this energy, to like fall near that, no? And the macro scale effect really is it adds extra energy levels to use in the energy bands. no? So meron kang extra energy level dito sa gitna that electrons can occupy in order to easier get to up here, no? So you essentially, this is what you would call indirect generation, no? The electron jumps to the RG center and then further jumps to the conduction band, no? And this is actually predominantly happening in silicon, no? We don't usually have direct generation and direct recombination in silicon. In silicon, we usually have RG centers, no? So ito din is also RG center. So in RG center recombination, the electron falls into an intermediate energy state caused by RG centers and then into a hole, no? Where then it combines, no? So yun siya. You can see here an example of kung saan lumalabas yung intermediate energy levels na binibigay sa atin ng silicon, ng impurities in silicon for different types of metals, no? So Au, aurum, gold, Cu, cuprum, copper, Mn, manganese, chromium, iron. These guys introduce their own intermediate energy states, probably in the d orbital. So nandyan sila sa gitna. So these can act as RG centers, no? So akyat sila doon, tapos akyat sila doon, no? So these are metal impurities create RG centers. Okay. Extra trivia, direct recombination is usually done by LEDs, no? Kapag by the way, LEDs, light emitting diodes, no? So this is usually the symbol for that. May light na lumalabas. But essentially, no, since the band gap for these semiconductors, no, itong dalawa sa baba, since the band gap for these semiconductors is almost equal to the band gap of to the are actually exactly equal to the energy content of the light, no? Kasi energy equals lambda h, where this is the wavelength. And for example, if the wavelength is blue, no, then this energy would be around 3.4 electron volts. And voila, that's the band gap of gallium nitride, no, which is used for the blue LED. No, the first LEDs made were actually gallium arsenide, infrared LEDs. So I imagine they had trouble telling people like, well, this is emitting light. It's just that you can't see it because it's infrared. But when they added phosphorus to it, it started emitting red light, and then people started believing them, I suppose. Anyway, next, no? So OJ, no? This is pronounced as OJ, the combination. So imagine, no, I had two electrons and they bump into each other, no? What essentially happens is the electron transfers its energy to the other electron, and one of the electrons gets promoted. No, it gains energy and it goes up. Meanwhile, the guy that gave it energy gets knocked down, no? Knocked down to the valence band, to a hole, no? To a hole that's available, no? This is called OJ recombination. One electron in the conduction band gains the energy that an electron loses from recombination, no? So, simple naman. Now, here's okay. So, what if walang hole na malapit? OJ recombination does not actually happen kapag walang hole na malapit, no? The thing is, what I interpret this as happening, no? It's easy to say that it's collision, but what actually happens is this thing fell. Eh, di ba sabi natin kanina, this thing is supposed to emit a photon. This photon was caught by a nearby photon, by a nearby electron, no? In the conduction band, thereby promoting it even higher, no? So that's what actually happened as OJ recombination. Next, we have impact ionization, no? So given na nangyari yung OJ recombination or through some other process, no? You could have given this guy an electric field, that's why it has a very high energy. it could bump into an electron, no? Kasi yung difference nila dito is not really a physical, like a location difference. It's a difference in energy, right? So if it passes over this guy in the exact same spot as the other electron, this guy pala rather, no? Then it could bump into this guy and give it enough energy to promote it, no? Of course, through that bumping, na-demote din yung mataas na, yung high energy electron mo, no? So now we have two electrons at the very edge of the conduction band, no? So that's called impact ionization, no? So you could interpret it as may electron ka, tapos na-impact niya yung isang electron and it managed to bring that electron up, no? And because the first electron was so high energy, it still is in the conduction band despite doing that, no? So it's impact ionization. In contrast, OJ recombination, this electron bumped into this electron, lost enough energy, it fell out of the conduction band, no? So yun yung nangyari doon. Alright, so with that, that ends our lecture for today, no? So summary, current can be moved around by electric fields and it causes drift current, no, by moving our carriers around with an effective velocity. Carriers also tend to move away from areas of high concentration. This is called diffusion, no? And diffusion current depends on the charge of the carriers that you use. And lastly, no, carriers are generated through generation and are destroyed through recombination, no? So with that, that ends our lecture for today, no? So any other announcements? Uble, you're probably in Uble already. If not, I'm going to resync and enlist the rest of the people who are in CRS to go to the Uble. Yung Uble natin, merong dalawang quiz doon about these two lessons and they will be open by Monday. You guys have 2 attempts, no? Next is problem set, no? Problem set will be released also sometime next week with a deadline in week 4, no? So matagal pa yung deadline. Bakit? Kasi the next part has 3 lectures for it. So hanggang week 3 yung coverage ng problem set kasi. All right. So ayan, with that question. When po deadline ng quiz? Deadline ng quiz would be the week after, no? The week so next week no Monday siya magbubukas, then the week after that na Saturday ang deadline. Dapat. Hindi ko pa sineset yung deadline to. So, pwede pang magbago. But at the minimum, that's the deadline. Sir, question lang po. Doon po sa previous lecture regarding doping, ano po yung sinisignify ng EF minus EI? Sige. So, go back to EF minus EI. Ito. Diba? Ang EF minus EI, it signifies this. No? By the way, guys, feel free to go. Ingat kayo sa travels nyo, no? Para sa susunod na klase or ingat pauwi kung kung uwi kayo, no? So EF minus EI is this difference, no? So we interpret this gap, no, between the Fermi energy level and the intrinsic energy level and put it in this equation, no? So the difference between the Fermi energy level and the EI, no? We say na proportional to that, no? So proportional to this difference, yung number of holes, number of carrier electrons natin. Does that make sense? So ginagamit natin yung difference between EF and EI to calculate the number of electrons, carrier electrons, no? Kasi tumataas yung number of carrier electrons kapag EF with respect to EF minus EI, right? Kasi also another thing, no, observe, no, if EF equals EI, we go back to the intrinsic carrier concentrations, right? So actually, this is just like extra, no? Dinagdagan mo lang siya. Sinabi mo lang na kapag tinaas ko yung Fermi energy level, madadagdagan yung number of electrons, right? At mababawasan yung number of holes, no? Which is what we expect naman kapag dinope mo, right? Ayan siya. So I hope that helps. Carrier electron, yes. Because kapag nasa conduction band siya, carrier siya, no? Likewise, itong nasa baba, these are carrier holes, no? It's the lack of an electron in the valence band, no? So these are carrier holes. Bakit? You could interpret kasi that the conduction band is full of holes because it's devoid of electrons, right? So yan. All right. Sige. So that makes sense. Then that's great. All right. Anyone else have any additional questions? All right. So if not, bye-bye WFX. Hello WFY. We will start in about 5 minutes. So mga 4:07.
Thank you po, sir.
Thank you.
Thank you,
Bye-bye.
sir.
Thank you po.
right? Hello. So Rafael, the the attendance is supposed to be done a little near the end of class. is, is why it has questions about the class, no? Anyway, kind of funny. But the questions are only really there naman kasi because of para sa student feedback, no, so that I know whether or not a lesson was way too quick, and I know that um because frankly some people answered na everything was difficult or tapos none was easy. So we can use that as reference, no, to try to increase the amount of content na nilalabas, no. uh but frankly, I'm also shocked because it's the first semester after I started trying to do these surveys sa Google form. And ang tinuturo ko last sem is 143, no, which is ano which had a lot more easy answers towards the easy part rather than the non-answer, shockingly. Anyway, sige. To the start, no? Hello, everyone. We kind of left off a slide after this Fermi level, right? So again, no? Sige na nga, let's go back to energy band diagrams. 'Di ba? Right? First of all, no, basta pala araw nyo, guys. Please, give me a thumbs up if you are still feeling well. Nako po. That's not a thumbs up. All right, sige. So, probably this is your last class of the day anyway, no? So, let's just push through it. Anyway, energy band diagrams, no? Sorry for doing this to you in their last class of day, but energy band diagrams, no? Blame Niels Bohr. If you zoom into the energy bands, no? At the third energy level, you find that p orbitals are actually a little bit higher than s orbitals, right? And smart people have solved where these energy bands are, and they found that as you gain more silicon, no, as you put them closer together and you have n silicon atoms arranged in a crystal, no, and these energy states actually go on start overlapping with each other, and essentially they become very dense, no. So meron silang states dito, meron silang states doon, no, and they find that there's like a part that's lacking in states, no, and yung equation na ginawa nila, no, to find the density of states is this equation, no, of which most of it are constants, no, so no need to be afraid of it. That's why I put this thing here, no, to show you guys that it is not that we come in peace, sabi niya, no, it's just a constant times this thing, basically. Anyway, the shape is square root, no, and we find that this thing, no, this equation has no real solutions sa gitna, no? Meaning there are no occupiable states for the electrons. Sino ba ang pupunta dun sa states? Yung electrons, di ba? They find occupiable states. That's what fermions are. No, electrons are fermions. They're that type of particle. They are the thin hoso na particle, no? Unlike protons, which are big, no? We call those hadrons. Anyway, fermions need to occupy states, no? And walang states dito sa gitna. That's why we call it the forbidden gap, no? And the band gap, no? And depending on the size of this forbidden gap, we classify materials. No? For insulators, these gaps are extremely large. For semiconductors, these are not very large, no? But like they are within the range that is that can be overcome with temperature, essentially. For metals, this band gap does not exist at all, no? Meaning it can conduct electricity no matter what temperature it is, no? So, what prevents really, no, insulators from conducting a lot of electricity? Well, actually, no, Heat zaps electrons upward in the energy band diagram, on average about 26 milli-electron volts, no? And where did I pull this number out? This is from Boltzmann's constant, no? Which is a thermodynamic constant, no? Boltzmann's constant is uh Boltzmann's constant is sorry about that one. Boltzmann's constant is a thermodynamic constant, no? Relating. Sige, so aside tayo. I know like maybe some of you have trauma hearing this term, but given a box of ideal gas, no? Yan, ideal gas. Opo. Um, Boltzmann related the temperature of that ideal gas to the amount of energy that each particle has, no? So each particle gains a set amount of energy, no? Depending on the temperature, no? And Boltzmann theoretically calculated this, and he found that it's around 8.617 times 10 to the minus 5 electron volts, no? Which is like proportional to joule, right? Actually, the real Boltzmann's constant is like joules per Kelvin, no? But we turned it into electron volts because electron volts is our measurement of energy, right? Anyway, this is the amount of energy that temperature gives each particle. And what's a particle? That's like an electron, right? Electron is a particle. Now, what's a particle para rather? An electron is a particle. So electrons gain this much energy from room temperature, which is 300 K, no? So if you multiply EV over K times K, no? You get 0.026 electron volts, no? Or 26 milli-electron volts per point at any given moment, no? On average. And this is just average measurement, no? So this can be a Gaussian distribution, essentially. So some particles actually get a lot more energy than usual, which is why it is likely that you find around 10 to the 10, no? Intrinsic carrier concentration. You find around 10 to the 10 electrons on the conduction band for semiconductors, but much less likely for insulators. Bakit? Because this energy is just too high na, no? For temperature to overcome. Anyway, how do we quantify this like temperature thing, no? How do we quantify how many electrons can we find in the conduction band depending on the temperature? Well, Fermi and Dirac, no? uh, solve this thing for you, no? This is the Fermi-Dirac distribution or the Fermi function, as Pierre's book calls it. No, ignored the existence of Dirac. Um, I don't know why, but anyway, this function is the probability that a state at a specific energy level is occupied by an electron. No, so then, for example, um, at room temperature, no, the shape is about like this, no, and it's an exponential shape, meaning it's never actually zero. It approaches zero as it approaches infinity, yes, but it's a very low number here, no? It's just a very low number there, which means that there is always a non-zero probability, no, at room temperature to find an electron somewhere here, right? Makes sense naman. At the same time, this is not exactly one here, right? As it approaches infinity, no, this thing this thing approaches infinity. It approaches one at infinity rather, not at negative infinity. But it never actually gets there. So there's like a very small chance of an electron not being in a state in the valence band, no? Which means we could find some holes here, no matter how small. Now, another thing, what happens at 0 degrees Kelvin, no? Now, this one is interesting because we're going to pull out the calculus, no? Actually, I'm not sure if it's defined as calculus essentially, but limits, no? Sige. So e to the e minus ef over kT, no? At as t approaches 0, no? So t approaches 0, to, no? So lim of that, and we find na 0 plus to. So it approaches 0 from the positive side, no? Now we have two cases here, no? If E is greater than EF, no? Positive yung nasa taas, right? So then, this would be a positive number over 0 plus, which means it's positive infinity. Other case, E is less than EF, no? So then, negative yung nasa taas, rendering this negative infinity, no? So what's E to the positive infinity? Infinity, right? Kasi pag ganun, si E, right? So 1 plus infinity, 1 over 1 plus infinity is 0, no? So at E above EF, no? This is 0, right? At E below EF, it's E to the minus infinity, right? And E to the minus infinity is what? 0, no? So 1 over 1 plus 0 is 1, no? So at below EF, the Fermi probability is flat 1, no? So what does that mean? Kung flat 0 to, there are absolutely no electrons up there. Kung flat 1 yan, there are absolutely no holes down here, no? So that's what happens to the Fermi function as we change the temperature, no? Right. Ngayon, given the Fermi function, no? The Fermi function is the probability that a state at a specific energy is occupied by an electron, no? So this is F of E. Ito, density of states, no? So this is GC of E and GV of E, no? It's the number of states in the conduction band, number of states in the density of states in the valence band, no? Bakit natin tinawag na density of states? Kasi ang units nito is number of states per cm cube, by the way. Pretty sure I noted this in that slide, but units niya is per cm cube, no? By the way, we're going to be focusing a lot on units this time because that allows us to remember formulas that we don't remember. Anyway, so probability that state is occupied times the number of states equals number of electrons. Because that's the number of occupied states, right? In the conduction band, for example. So kapag minultiply mo to, doon, you get the number of electrons, right? So Fermi function times GC of E, no, times density of states in the conduction band equals the number of electrons in the conduction band per energy level, right? Does that make sense? Likewise, no, if we take the probability, no, probability that state is not occupied, then ano yung kailangan natin gamitin? 1 minus F, di ba? 1 minus F because it's the probability that a state is not occupied, which is the opposite of Fermi probability, no? And we multiply that to the number of states available in the valence band, we get the number of empty states in the valence band, which is the number of holes as a function of E, right? So one additional thing that we could do here is if we integrate this function, no, over all energies, we find the number of electrons in the conduction band, no? Total electrons in the conduction band, no? So if we integrate this from EC, no? This EC, right? Conduction band to infinity, then we should get 10 to the 10, right? So confirm for yourself. Actually, no. This integration is actually quite hard to do. It's integration of a square root function times a itong density of states yun times 1 over 1 plus e to the x, no? So even I don't know how to integrate this off of the top of my head because it's been so long from calculus. But you know, if anyone you want to try to get an analytical solution, feel free to try. But you know, I would rather use Python or MATLAB, for example, to do this integration for me. But it should be 10 to the 10. Likewise, no, if you do this for holes, no, it should also be 10 to the 10. No, if you integrate the probability that a state is not occupied times density of states at the valence band, then you should also get 10 to the 10 at room temperature. No? So yeah, that's carrier concentrations for you. Right. Next, doping. No? So when we dope our silicon, right? Doping. No, what is doping again? It's the controlled addition of donors or acceptors. No? What's an example of a donor? What's an example of an acceptor? Boron. No? Boron is what? It's an acceptor. Tama. A donor, phosphorus. No? So, to be honest kasi maraming estudyante na biktima kasi parang NDNA lagi sa mga lecture dati tapos biglang pagdating sa exam sabi, dinope ng boron. Yan, patay. Ano ulit yung boron is what happened. So, you know, some of the smartest people I know got victimized by that one. So, you know, let's remember that boron is an acceptor and phosphorus is a donor. Anyway, kapag nag-dope tayo, we reasonably expect, right? Kapag nag-dope tayo ng donors, dadami yung number of electrons, right? Sa conduction band, no? So then, lalaki yung bump dito. Tapos, liit yung number of holes. Bakit? Kasi, P is equal to Ni squared over N, di ba? So then, if N gets larger, P gets smaller, no? So then, we do expect reasonably na bababa yung number of holes, no? Intuitively, since yung number of electrons in the conduction band is kind of, right, proportional to how far along, like how far upward the Fermi level is, kasi that's the probability that there's an electron there at all, right? Then we could represent really that we could represent the carrier concentration in terms of how far up the Fermi level is relative to where it was before, no? So then we define this new energy level, we call it the intrinsic Fermi level, no? So bakit natin pinangalanan ganun? This is the Fermi level at intrinsic carrier concentration, no? So kung 10 to the 10 yung number of electrons mo and 10 to the 10 yung number of holes mo, right? Then this would be where your Fermi level is, no? Kung undoped ka, then your Fermi level would be exactly here, right? Now, remember, di ba dati, our carrier concentrations used to be N equals Ni and P equals Ni, right? 10 to the 10 parehas. Ang dinagdag lang natin, meron lang tayong correction term. Magdadagdag tayo na we say is exponentially proportional yung carrier concentration natin, no? So our N, no? N is proportional to E to the difference between the EF minus EI, no? Over KT. Yun ang sinasabi natin, no? So, it exponentially increases, no? The number of electrons exponentially increases as you go further from your intrinsic energy, intrinsic Fermi level, no? So, yun na. That's something that we would like to know, no? This is the new equation for that. Conversely, no, kapag binaligtad mo yung equations, you find na the the difference, no, the shift in the Fermi level can be derived by the shift in the Fermi level can be derived by KTLN of the number of total electrons over Ni. And bakit natin i-represent in terms of this, no? Kasi usually, mas alam natin kung ilan yung number of total carrier electrons kesa sa shift in Fermi level. Kasi parang, ano yung shift in Fermi level? We don't know that yet. What we do know is N and P. Bakit? Kasi meron tayong equation for that, right? Ano yung equation for that? Depending on the dopants, it's Nd minus Na over 2 plus square root of, this is N by the way, babalik mo sila kapag P, Nd minus Na over 2 squared, no? Plus Ni squared. Yes. No? So that is the equation for that, right? So then we substitute this into this and we find that we find the shift in Fermi energy, right? Same with holes, no? So depending on the concentration of electrons or the concentration of holes, we can find the shift in the Fermi energy level, no? And we could also use, no, the energy band diagram representation for our own good, no? We can build an equation around the position of the energy band, of the Fermi level, no? So what do I mean by this? You can think of the Fermi level as a sort of sea level, no? Sea as in dagat, no? Where electrons and holes alike both really want to be near the Fermi energy level. So kapag lumalapit si Fermi energy level to one of the bands, dadami yung carriers doon. And conversely, uunti yung carriers kung saan siya mas malayo, no? So if for example, in this, I had a P-type semiconductor, tas nandito sa baba yung EF, then I would have very few electrons in the conduction band, but a lot of holes in the valence band, no? Does that make sense? Anyone have any questions about doping in EBD? Yes?
Sir, confirming lang, Ni is yung original carriers ba?
It is the intrinsic carrier concentration, yes.
Sige po. Tas may Pi din po ba, sir? Or same
No.
lang, Ni
So,
lang talaga?
essentially, yes. You can think of it as Pi as well, yes. So,
Sige, sir.
intrinsic hole concentration, same.
Sige, sir. Thank you, sir.
All right. So, yeah. That's the Fermi level is like something that the carriers want to be really close to, is what it is. No? Previous equations ng concentration na may square root. Ito is energy band diagram na siya. That's what's special about it, no? And we will find na, okay, so maybe the question is more like, so bakit natin kailangan ng energy band diagram? We just came back to the original equation, no? Alam na natin yung N. In-integrate natin yung energy band diagram, we got Ni again. But we knew Ni to begin with from experiments. Well, the thing is, no? When we start building bigger semiconductors, devices, no? Like your diodes, saka magsha-shine yung energy band diagram. So, we're still building up to it. Next Wednesday, it'll all come crashing down. Anyway, no? So, um, and sige, anyone else have any questions about the EBD? The more exact answer to kung ano yung kaibahan niya is ito, no? So, this is exact concentrations. But you could also represent this as EF minus EI over KT, no? So, yun lang din siya. So, it's both calculating the same thing. One is relative to the Fermi energy level. One is relative to the given donor concentrations. So, sample problem might be given a position for the Fermi energy level, find ND minus NA. Ayun. So, that's one thing that could happen in an exam. Yung Fermi level po ba, electrons lang po kino-consider niya or pati po yung holes? Yung Fermi level, it also considers the position of holes. Essentially, kung nasan si Fermi level, it affects both electrons and holes, right? Kasi ito, di ba? EF minus EI, tas EI minus EF. Ito. Actually, if you combine these two equations, you still also find that NP equals NI squared. Which is the relation to begin with, right? So the position of the EF affects both holes and electrons, no? So kung nasan si EF, dadami yung carriers dun sa part na yon. Tapos kung nasan malayo si EF, onti yung carriers, no? So in this case, dahil mas malapit siya sa conduction band, mas marami yung electrons kaysa sa holes, no? Which is what you expect because we shifted this up by adding donors from doping. Unit of the electrons and holes, no? So this is the 10 to the 10 per cubic centimeter, no? So if I were to give you a cube of silicon, this much, no? You could give that to someone and say, there are exactly 10 to the 10 carrier electrons in that cube at room temperature, no? Assuming it's intrinsic. Yeah. So, sige. Let's move on, no? Last part of this first lecture, no, we're degeneracy, no? So if you add too many dopants, no, to a semiconductor, you turn it into a metal. Bakit? Because there's too many carriers. Wala ka nang heat, no? Ang dami mo pa ding carriers, no? So it essentially turns like a metal. And Pierre, in his book, defines this degeneracy as if you are within 3 kT of the conduction band edge or the valence band edge, yung EF mo, no? 'Di ba? Kapag nag-dope tayo, gumagalaw si EF. Right? That's what we settled last slide. If you dope too much, lalapit na lalapit si EF sa edges ng conduction band at saka ng valence band, no? And at some point, magiging degenerate na yung semiconductor mo. And we don't like that. I may have defined it as turning it into a metal in this case, but it's more like masisira yung assumptions natin, no? Hindi nagagana yung mga equation na meron tayo. Like these equations in this previous slide, hindi na sila gagana because of degeneracy, no? That's why we don't like it. And Pierre says na it's if yung EF mo is within 3 kT na of the conduction band. Now, we can derive this, no? Does anyone remember yung band gap ng silicon? What is the silicon band gap? What is this? (1.12 electron volts. Correct. So what's half of that? This is 0.56. Right? So we have that as reference, no? 0.56 minus 3 kT, no? So 3 kT is 0.026 times 3, right? It's about 78. So if you add that to 0.56, you get, if you, rather, you subtract, no? So negative this plus 0.56 electron volts equals, eto, no? 0.482 electron volts. Bakit ko kinalculate to? Now we know that this distance is 0.482 electron volts. Eh ano yung distance na yon? That's EF minus EI at degeneracy. No? So, I substitute that to the equation, no? KT ln N over Ni, right? Was the equation for the Fermi energy level, right? And I find na solving for ND, we find that doping on the order of 1.12 times 10 to the 18 is degenerate, no? So we consider Na or Nd greater than 10 to the 18 degenerate. No? So it may be 1.12, but consider anything on the order of 10 to the 18 degenerate na. No? Now, okay, one extra thing, no? Can anyone identify an assumption that I used for this part? So, yung original equation natin is KT ln something over Ni, right? Ano yung something na yun? N, right? Kaso ang ginamit ko ND, no? So ang assumption natin is that ND is much much greater than Ni and ND is also much much greater than Na, no? Because those are the requirements for N to be equal to ND, right? And bakit valid yun? Because we are trying to derive for degeneracy. Eh to be degenerate, 10 to the 18 ka na. Kung 10 to the 18 ka, that is much, much greater than 10 to the 10. That's an order of 8 times increase in magnitude. No? So, this is valid. This is a valid assumption. Alright? Sige. So, that's the end of that lecture. Card. Right. Sige. So, let's take a 5-minute break and then we'll continue with the rest. No? If you have any questions, no, feel free to ask questions right now. Sige, Emil, what's up?
Hello sir. Kailan po i-release yung problem set po?
Problem set, I'll probably release it sometime next week. Week 4 pa naman yung deadline eh, so that's great. You're going to have at least like around 1 week to do it. Like 1 weekend and a week. Tapos the Saturday of the next weekend, saka siya isasubmit.
Okay po, sige. Sige po sir. Thank you po.
Alright? Alright, sige. For week 1B, let's talk about carrier action. No? So, what does it mean when we say carriers? These are your electrons and holes, right? Action is what they do, no? So let's talk about what electrons and holes do, no? So first off, let's talk about drift. So we know from physics 7.2, yes, right, that an electron, or rather a charged particle, no, when put in an electric field, experiences a force depending on the direction of that electric field, no? It's proportional to the magnitude of the electric field and the charge of the particle, no? For electrons, since these are negatively charged particles, the electrons go the opposite direction of the electric field, right? For holes, they go in the direction of the electric field because they are positively charged, right? Now, for situations in semiconductors, no, uh, this is a little more complicated, no? Bakit? If you were to apply an electric field, no, to a free particle without anything blocking its way, it's going to accelerate infinitely, no? It's going to accelerate forever and ever until it reaches speed of light or something like that, right? For an electron inside a silicon lattice, it kind of bumps into everything, no? So for example, you have this electron here. You apply an electric field, it starts going that way, no? But because of heat, no, it kind of starts wiggling around, right? Because heat is vibration, no? Because of that, it bumps into every silicon that's blocking its path, no? So then, what happens to the electron is, okay, we start the electric field, accelerates, 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 and then it bumps to a silicon atom. So it loses all of that speed, no? And then it starts accelerating again. And then it bumps again to a silicon atom. And again, it loses all its speed. And the cycle goes on and on, no? So it's kind of like a car in traffic is what happens, no? So yeah, electrons keep bumping into the silicon lattice, no, the silicons in the silicon lattice, and it keeps losing all its energy, no, while traveling. And the bumping, no, is called scattering, no. And when it's happening against the silicon atoms in the lattice, you call that lattice scattering, no. Now, we also have this thing called dopant scattering, no, because if you dope, no, and ano, uh, semiconductor, no, you have not just silicon, but also, say, for example, phosphorus. By the way, no, kung phosphorus, anong type ng semiconductor to? Kung phosphorus yung dopant, what type of semiconductor is this? E, no? E yung dinagdag. So, it's a donor, yes. So, ano yung type nung semiconductor? Is it N-type or P-type? N-type, yes. Tama. So, it's an N-type semiconductor. Kasi donors yung nilagay natin, no? So, it may be misleading na phosphorus yung nakalagay dito kasi P yung phosphorus, but phosphorus is a donor, meaning it gives electrons, meaning it makes the semiconductor N-type, no? So, that's something about it. Anyway, since phosphorus is a donor, right? It starts off with 5 valence electrons and then it loses it along the way, no? Umalis na yung electron na yun. So then, since phosphorus has an atomic number of 15, it has 15 protons and started with 15 electrons, but now it only has 14. So there's actually a net positive charge here. So then, what happens is, even if the electron was just going to barely miss this phosphorus atom, starts curving a little back to it. Kasi it's positively charged. The electron is kind of attracted to the phosphorus. No? Which means that effectively, mas likely na tumama yung electron sa phosphorus kaysa sa silicon. So, dopant scattering actually is worse than lattice scattering. No? And those are the two types of scattering. Now, okay, sige. So, hindi ko na cover to dun sa last class, no? And we're also losing time here, so maybe not. So, type of scattering, no? One of the most famous experiments in physics is Rutherford's alpha scattering experiment. Kasi at the time, di ba, um, akala nila atoms were like this, no? It's like a pie made up of protons and electrons, no? It's just all scattered together. The guy who proved na there's actually a nucleus in the middle and the electrons are actually around it is Rutherford in the alpha scattering experiment. So this thing emitted alpha particles, which is, by the way, glorified term for helium, no? It emitted alpha particles, tapos tumama siya dun sa gold. And they found na most of it actually goes through, no? Because there's not enough material in the middle, no? Nakakapasok pa din yung, nakaka-penetrate yung helium. But sometimes it violently deflects, no? So they theorized na that's because there's a very hard thing in the middle of a cloud of electrons, no? And that's why we know that atoms have nucleus, no? Because of scattering. Anyway, and that's why it's called scattering, no? Because, you know, these things literally scatter. Anyway, again, no? Electrons accelerates, bumps, and then accelerates again. It's like something stuck in traffic. And what we know about things stuck in traffic is that they take around 3 hours to get to QC effectively, no? From Laguna. So, just like that, there is also an effective velocity for electrons, no? And holes as well, no? So, everything also applies to holes. If we apply an electric field, we get an effective constant velocity. No, we get an effective velocity because of this acceleration and bumping action. There's just an effective constant velocity because there's a mean time between collisions, is what we know. So then we can define that as a constant drift velocity Vd, no, for both holes and electrons, no? So given a bunch of carriers moving in a direction, no? The total number of carriers passing through a cross section, no? So take for this cross section, for example, no? The total number of holes passing through this cross section at any given moment is velocity, no? The velocity of a hole, no? Which is VdP times the number of holes per centimeter cube times the cross-sectional area equals number of holes per second, no? So if you do the dimensional analysis, no? So this is cm squared area, this is per cm cube concentration, and this is cm per second, no? Magka-cancel yung lahat ng cm, you get 1/second, no? So the number per second, no? Likewise, you could do the same math for electrons, right? Anyway, the important thing about that is we get these, which is the number of carriers per second, which means that since each hole is charged positive Q and each electron is charged negative Q, no? Then we find the total amount of charge crossing a cross-sectional area at a specific point in time, no, per second, which is this. Charge per second passing a cross-sectional area that is what we define as current, no? So these are our equations for current. Negative dapat to. Also negative din dapat to, no? But yes, we just multiply Q, we get that back, no? Q that we multiplied is the charge of an electron. Holes are positively charged, electrons are negatively charged, no? So hope that's all clear for this one. So since we get so okay, we're talking about, we theorized, no, merong effective drift velocity, no, merong constant velocity effectively kasi it keeps bumping. So then we asked the experimental physicists pa-measure, no? So they did, no? This is a measurement in ultra pure silicon. So that is silicon without without dopants, without impurities, no? And they find that there is actually an approximately linear relationship between the strength of the electric field that we apply, no? Remember, we applied an electric field to induce movement in the carriers, no? That's the only reason we're talking about anything right now, really. And we find that there's actually a linear relationship between the field strength and the velocity, no? The effective drift velocity of the carriers, no? So since it's linear, there is a constant of proportionality, no? And we call those constants of proportionality the mobility, no? It's the carrier mobility. So for silicon at room temperature, 300 K, no? Intrinsic silicon is, mobility of electrons is 1350, mobility of holes is 480. So that's it. That is effectively what we use. That's what the experimental physicists told us they measured, no? Now, another thing to note here is saturation. Actually, as you increase the electric field strength, they don't get infinitely fast, of course. At some point, they bump too much because they move too fast, no? They bump into too many silicon, too much, they bump too much, no? They scatter too much. And so the velocity actually saturates at some effective saturation velocity, no? So I'm gonna ask you guys, what do you think this means for the mobility, no? First off, how do we get velocity, no? The mobility from this graph. This is a graph of velocity versus electric field, right? So what is mobility versus electric field? I just say this mobility is the slope, right? Because it's the constant of proportionality of a linear function, then mobility is a slope. So then to get the slope, mobility is equal to the derivative of the velocity over with respect to the a change in the electric field strength, no? Actually, walang araw to. Electric field strength is the magnitude of the electric field, right? So that is how we get the mobility. So then, what saturation means is that it starts off fairly constant and then it drops hard to zero, no? So pag ganun siya, ang carrier mobility, no? With respect to electric field. So that's one thing I wanted to point out. But for the purposes of this course, we're going to assume that mobility is quite constant, no? Hindi tayo nagsasaturate. Because electric field strength of the magnitude 10 to the 4 above is actually quite a lot, no? That's power electronics level, not integrated circuits level. Anyway, what affects mobility, no? So shown here are just demonstrative graphs, no? They come in piece. Of course, kapag kailangan nyo siya for a calculation, they will be given. No, you don't have to memorize graphs because who memorizes graphs really? The only graph you need to memorize is x squared looks like this. X squared looks like this. E squared looks E looks like that. 1 minus E squared, something looks like that, which is the Gaussian distribution, ganun. But anyway, uh, this type of thing, so against total impurity concentration, no? So what's total impurity concentration? Impurity meaning dopants, no? So total impurities meaning your total amount of dopants, no? Na plus Nd. Now, against the total concentration of impurities, no? Mobility reduces. Bakit? Because we've discussed earlier, dope at the carriers scatter against dopants, right? So if there's more dopants to scatter against, it hinders the mobility, no? So then electron and hole mobility get lower as you increase the number of dopants, no? Likewise, the mobility also decreases with increasing temperature because of lattice scattering. As I said earlier, no, the electron, the only reason that, well, part of the reason why it starts bouncing around with everything is because of temperature moving it randomly, right? As you increase the amount of temperature, the silicon actually starts vibrating as well, no? So then it's more likely to bump into silicon as you increase the number of, the amount of temperature, no? So an increasing temperature also decreases the mobility. Sir, bakit po magkaiba ang mobility ng electron sa hole? That's because holes essentially ano ba yun? Meron ba akong picture nun dito? So a hole is essentially like that, no? So you can think of it this way. It's harder for a hole to move around because it needs to also rely on the probability that an electron decides to leave its current energy state to go to the hole, no? So it's like ano ba? Wala akong maisip na ano eh, kagandang analogy, but you can think of it as like the electrons need to squeeze through um parang unavailable energies in order to occupy the spot of the hole so that kasi effectively no, yung hindrance for the mobility of the hole is the scattering na nangyayari dun sa electron na mag-occupy ng hole, no? It's not the hole that's scattering into anything, it's the electron that's going to occupy the hole, effectively moving the hole, no? That's scattering against things, no? And I guess a way to put it is because these things are in the valence band, there's they're much closer to the atoms, no? They're in much lower energy levels, right? Kasi they're in the valence band, no? Which means that it's easier for them to hit the um atom itself, no? To scatter onto the atom kasi they're much closer to them kasi they're in the valence bonds, right? At least that's what I interpret the difference in mobility is, no? In general, yes, it's because the electrons need to squeeze through in order to occupy the hole. That's why effectively mas mabagal mag-move ang holes kaysa sa electrons when it comes to drift. Ayan. So anyway, continuing on, no? We can measure resistivity now then, no? Because since we have an electric field, right? Given an electric field, no? Or rather, since we've been talking about an electric field, paano ba gumawa ng electric field? We apply a voltage across a specific length, no? So given a voltage across a specific length of wire, kung 1 volt to, 0, tapos ground yon, no? Tapos 1 cm yung wire, edi that's 1 volt per centimeter constant electric field dun sa length ng wire, no? That's how electric fields are made. So, since E is volts per centimeter, then we can substitute the equations for IN drift and IP drift in order to do this, no? Ah, yes, tama, tama. Drift velocity. Tapos, okay, sige. So, may hindi pala ako na-discuss dun sa class kanina, no? Um, kanina, yung IN drift natin was QN VDNA, right? Because VD is mu N E, right? Now, since the drift velocity of an electron is opposite the direction of an electric field, right? Magkakaroon ng extra negative to, right? No? So yung negative kanina, remember, no? May negative dito, right? To, may negative dyan. So then, ito dapat is negative mu and E, which means that this is going to be positive, no? So positive yun. I'll probably clarify this in an additional document before Monday kung ano, because the signs are apparently screwed up in this set of slides. Anyway, since we know that the electric field is V over length, then we can relate the total drift current to voltage over resistance, no? We just replace E with V over L, like here, no? Tapos, we replace the total current, which is IN plus IP, no? Current due to holes, current due to electrons, with we add those together to get the total current, and we relate that to the resistance, no? So we solve for the resistance here. No, resistance here would be uh, L over A times this thing, no? And we know a definition of resistivity, no? To get a resistance of a arbitrary size of a block of material, no? We use the resistivity, no? So if you if you equate this equation against rho L over A, you find an equation for the resistivity of a semiconductor, no? Depending on the number of holes and electrons, no? So this one, I assure you, the signs here are completely correct, no? So Q P mu P plus N mu N, no? Now, important thing to note here is if you try to do your units tawag dimensional analysis here, what you get is yung P mu P na lang, no? So P mu P, no? Q P mu P. This becomes Coulomb, cm squared, tapos cm squared din dito sa cm cube pala dito sa sa hole, cm squared over volt second, no? So then you get Coulomb per centimeter volt second, no? And the thing is, no? If you guys have ever examined the compound unit, that is the ohm, no? The ohm is actually equal to a volt second per coulomb, no? Because it's equal to a volt over ampere, no? So then, the unit of resistivity is actually 1 over ohm cm, which is ohm cm, no? So remember your units, no? We actually do have to pay a little more special attention to units than usual in this course. Bakit? Kasi centimeter tayo lahat, no? And units like the joule, no, are defined in terms of the meter, no? So that's something that you have to be careful about. You have to make sure that all of the electron volts cancel out and such. All right? Sige. So that's it for resistivity, no? Next, let's move on to diffusion, no? Um, this is the example that I used, no? But imagine a smoke belcher, no? the smoke belcher releases a lot of smoke and it starts dispersing into your entire neighborhood, no? Disperses into your house, follows you into the bathroom and such like that, no? And that behavior by particles is actually known as diffusion, no? Because particles tend to want to spread from higher concentrations to areas of lower concentration, no? So then, carriers actually have the same uh, behavior, no? Carriers, when they are in, when their concentration changes along the silicon, no? So for example, we have a one-dimensional block of silicon, we have a carrier concentration here. If there's a lot of carriers in the middle, they will diffuse outwards, no? So you will have a net flow of carriers this way and this way, no? So what happens is, no? Um, if okay, I'll split this into two, no? If our carrier, no, was an electron, no, if the majority carriers were electrons, what happens here, no? Electrons will be moving away from the middle, right? So pag ganun sila. So ano yung direction ng current? Well, electrons are negatively charged, right? And the current is the direction of the flow of positive charge, no? So then, the current goes in this direction, no? And vice versa, the current will also go in this direction here, no? So if this were a concentration of electrons, ganun yung current. Now, let's talk about holes, no? If these were holes, then diffusion will behave the same way, no? Things tend to diffuse to areas of lower concentration, no? So your holes will go here and your holes will go there, no? But since holes are positively charged, the current will go in the direction of the holes, right? So depending on your carrier, no, the diffusion current actually changes in direction because their charges are different, no? All right. So I hope that one makes sense. So let's start talking instead about the qualitative part of this, quantitative part of this rather, no? So the diffusion current density, no? Current over area, pretty sure this was talked about in Physics 72. The diffusion current density is proportional to a proportionality constant. That is the diffusion coefficient is what you call it, no? So we say that diffusion happens. No, we relate to the diffusion by taking the derivative of the concentration. Now, for example, the slope here is positive, so the derivative is positive. No, so for example, if our carrier was electrons again, then since the slope is positive, tapos pag ganun yung direction of movement ng electrons natin, then the direction of movement, the effective movement of the electrons is negative dn times dn over dx, right? Kaso, since electrons are negatively charged, you multiply that with q, no? You multiply that with negative q, and you get q dn over dx, no? So that's that one for this one, no? Deriving it for P is an exercise left to the reader, but you will just find na hindi na cancel out yung negative, right? Kasi positive Q to, no? Yun lang naman yung difference. Anyway, we know what DTN and DP and DN are for silicon, for intrinsic silicon in equilibrium because of Mr. Einstein, no? And Einstein derived this for us, but if you check your book, and actually Wednesday next week, we will find that we can derive this ourselves. No, it's actually quite easy. It's actually quite understandable, or rather than easy. But anyway, the exact relationship is more that you could derive the diffusion coefficient by multiplying the mobility of that carrier. No, so the diffusion coefficient for that carrier, you can derive it from the mobility of that carrier multiplied by 0.026 volts. No, 0.026. I told you, you guys will encounter this a lot. This is kT over Q. No, so since kT is 0.026 electron volts and Q is equal to E, no, so that's E over E, mag-cancel yung E, right? So this is mu n times 0.026 volts. And likewise, that's how you get the P-type diffusion coefficient as well. Right. So um, a macro scale experiment that you could do to see what diffusion actually does is the hot point probe experiment. No, so it used to be that there was a lab class. There is a lab class that's done at the same time as this course. No, but the thing is, you use a hot probe of your multimeter and touch a silicon block with it. No, so usually actually, eto, square yung silicon block na binibigay dun sa lab class na yon. And you touch your multimeter here and you touch your multimeter there, no? What happens is kapag hot yung multimeter mo, 'di ba? Heat causes the generation of a lot of carriers, right? So what happens is when you touch the silicon with your hot probe, dadami yung carriers doon. So then now there's a difference in the concentration of carriers across your semiconductor block, right? So kung may difference, may diffusion, no? So let's analyze the diffusion. Kung ang majority carrier, no, kung P-type yung semiconductor mo, no, so P-type, this one is N-type. So kung P-type yung semiconductor mo, holes would go this way, no? And so, kung kung holes are going that way, then the current is going that way, right? In the semiconductor. So to complete the circuit loop, current would be flowing that way through your ammeter, right? Which means that your ammeter will be saying, it's going this direction, so negative yung current. And that's how you tell it's a P-type. That's how you're able to tell it's a P-type semiconductor. Likewise, no, if it's an N-type semiconductor, this would be electrons, no? Electrons yung dadami, right? By the way, little detail, no? Dumadami din ang holes, right? Because they're also carriers. But on an N-type, there's definitely much more electrons than there are holes, so na-drown out yung current due to it, right? Anyway, electron diffusion goes to the right, no? Which means that the current is going this way, no? So to complete the loop, pag ganun yung current through the ammeter, making this a positive current, no? And that's how you tell between an N-type semiconductor and a P-type semiconductor via hot point probe experiment, no? Though you don't usually do this kasi semiconductors tend to be used in very, very small scale. Yun nga lang. This is like an experiment that you could. Typo lang yung negative sign sa N-type. Yes, sorry about that one. Okay, so any questions about diffusion before we go on to RG, which is the last lesson? All right, if not, I'll be going on to RG, no? So RG stands for recombination and generation, no? So in RG, carriers are generated or annihilated, essentially, no? So there's the types that we're going to be talking about, direct generation, no? This is when the electron jumps straight from the valence band to the conduction band because it absorbed energy. Energy from what? Heat or light, no? Now this is interesting, but we're not going to be covering it. But it used to be now that in this class, discuss natin theoretically, if you shine a laser onto the silicon block, actually dadami yung like like in the same way na nangyayari tong hot point probe, if you shine a laser into a silicon block, dadami din yung carriers because you're giving energy. So napopromote sila lahat. So direct thermal generation yun. If it absorbs a photon or it absorbs a phonon, which is like the quantum of heat, no? Then it jumps directly through the band onto the conduction band, no? Through the band gap into the conduction band. Likewise, if an electron and a hole meet, the electron falls into the hole, no? But it has to lose energy to do that, which means that this type of recombination, no, when they meet, that annihilation happens and a photon comes out, no? So the electron has to lose energy, so a photon comes out, no? In the same way that it happens for chemistry, no? So when an electron is demoted from one of the higher energy levels, then it's ano, then it's then it ang tawag? Then it releases it releases a photon, no? Of the energy difference between these two energy levels. So yan lang yung direct thermal recombination and direct thermal generation. And note direct. Bakit? Kasi we've been simplifying things, no? This doesn't actually happen that much in silicon, no? What happens in silicon most often is RG centers, no? Because of very small imperfections in the in the silicon lattice, no? Yung we call those imperfections RG centers because they introduce weird middle of the band gap energy states, much less dense than the other than the states that you find in the valence band and the conduction band, but they're still there, no? So those states being there mean that the electrons can actually jump onto it before going to the conduction band, no? So this is the predominant method, the predominant way in which the electrons actually get promoted to the conduction band in silicon, no? So what are examples of RG centers? Imperfections like missing silicon atom or extra non-silicon metals, no? So for example here, we have guest energy levels from the 3D orbital, no? Appearing here, no? In the band gap of silicon. So manganese introduces 3, chromium introduces 1, iron introduces 2, no? So electrons from down here could just jump into this gold and then jump into this gold again and go up to the conduction band, no? So this is the predominant manner in which silicon creates carriers, no? Now, so kung ito yung ginagamit ng silicon, sino gumagamit ng direct recombination and direct generation? That's usually done by LEDs, no? So the exciting thing about this is yung mga semiconductors na ginagamit natin para sa mga LED, yung band gap nila is actually almost as like almost exactly as high as the energy that the photon, that the color of light that it creates has, no? Kasi and that's what Planck's constant is, 'di ba? It's the Planck's constant relates the wavelength of light, which is related to the color, to its energy, right? So this energy for blue light is actually 3.4 electron volts. And voila, the band gap of gallium nitride, which is used for blue LED, is exactly 3.4. The same way, no, sa red na LED for gallium arsenide phosphide, it's 1.98, which is almost exactly the one for red LED. Now, interesting bit of trivia about this is that the first LEDs were infrared LEDs, no? So that's just gallium arsenide of around 1.8 electron volts. So masyado mababa yung wavelength to be actually called red, no? It was invisible light at the time. Infrared pa lang siya. So you can imagine they probably had a hard time convincing people that their diodes were actually light-emitting diodes. Kasi hindi naman nakikita yung light, no? It's infrared light, right? Which I guess was probably kind of funny trying to convince people na LED yun. Anyway, the next few types are compound types essentially, no? So they're special situations. One thing is called OJ recombination, no? So when two electrons meet and they bump into each other and both of them are low energy, no? They're low in the conduction band. One of them gains the energy from the collision and one of them loses the energy from the collision, no? So what happens is that one of the electrons gets promoted higher in the conduction band and one of the electrons falls into a hole in the valence band, no? So one of them recombines and one of them goes up, no? That's OJ recombination. Next is also about collision, no? Electron-electron scattering is what you call it. This next happening is when an electron very high in the conduction band meets an electron that's low in the valence band pa, no? If those two collide, the electron that's high in the conduction band goes down to just in the conduction band, but it gives a lot of energy to the hole that to the electron that's in the valence band enough to promote it, no? So what the ending is they're now both just barely in the conduction band, but they're still both in the conduction band, no? And we call this impact ionization because it's like the very high velocity electron high in the conduction band, no, hit that electron so hard that it popped it out of the valence band, no? So that's impact ionization and OJ recombination, no? And with that, so ends our lecture for today, no? So other announcements, there are 2 quizzes in UGLE na magbubukas yun sa Monday. Just remember that, just do take note of the thing that's noted above the quizzes na pwede kayong mag-type in the form of scientific notation. And problem set will probably be released sometime next week, no? Okay. So, yeah, with that, ingat kayo pa uwi or ingat kayo papunta sa sunod nyo class. Hopefully not, no, 5:30 to 7. All right. So, I'll continue addressing, no? So, apparently some people, including the previous class, no, one of the more unclear portions of of today's lesson is apparently yung doping in energy band diagrams, no? So actually, uh, oops, nakita yung aking preparation. Sige, let's start talking about yung Fermi energy levels, no? So let's take for example, 'di ba? To. So kung yung EF mo is nandito sa gitna, no? This is an intrinsic semiconductor, no? This is intrinsic silicon. So if I tell you guys that this is silicon, how many electrons would be up here? 10 to the 10, right? Which is Ni, no? Intrinsic carrier concentration. How many holes would be down here? 10 to the 10 as well, right? Intrinsic carrier concentration, no? So that's case 1. This is intrinsic, right? Case 2. I-label ko na si EI because that's where EF was back in intrinsic semiconductor, right? Tinaas ko si EF, no? So now what happens is N is now something greater, no? Something on the order of like 10 to the 15, no? And now P would be something like 10 to the 5, no? Kasi mas malapit na si F sa taas, no? And what type of semiconductor would this be? It would be N-type, no? Alright. Tapos, next case, P-type, no? So EI is here, EF is here, no? So then, the number of holes would be a little bigger, no? We would have 10 to the 15, thereabouts, right? We have 10 to the 5 electrons, no? For a p-type, no? So wherever EF is, dadami yung carriers dun sa band na yon. And carriers in the valence band are holes, carriers in the conduction band are electrons, no? All right. Now, paano ko nalamang 10 to the 5 yung electrons? Because it's Ni squared over the number of hole, which is 10 to the 15. No? Right? Okay. Now, given the number of holes, which we assume to be 10 to the 15, let's try to find kung nasan si EF, no? Relative to EI. So, P is equal to Ni, no? That is 10 to the 10. Sige, E to the EF minus EI over KT. So, that's 10 to the 10 times E to the EF minus EI, no? Which we're solving for over 0.026, no? So, moving the numbers around, we get 0.026 ano to? EF, EI minus EF pala, no? For holes. So, EI minus EF is equal to 0.026 ln of 10 to the 15 over 10 to the 10. No? So, this exact value, if we calculate that, would be this distance. No? And if we do that for this example up top, we would find that EF minus EI is equal to KT ln N over Ni, which would be 0.026 times ln of 10 to 10, 10 to the 15. No? Kahit po ba nasa EV, carrier pa din po yun? Yes. Kasi, sige. So, let's clarify this one, no? So, dun sa valence band, you have a lot of electrons, but you don't care about any of them because they're not carriers. They're in valence bonds. What do you care about in the valence band? It's the lack of electrons because the lack of electrons in the valence band are holes, no? And that means carriers in the valence band are holes, no? In the conduction band, your carriers are electrons. It's like you have a lot of holes in the conduction band, but only some electrons, no? And those carriers are electrons, no? So yun lang naman yun. By the way, feel free to go. We're just like recovering the unclear portions, no, and also answering questions, no. So feel free to go. If you have a next class, if you are rushing to go home, or because it's fairly understandable work study balance, no. Just addressing addressing concerns, if ever. All right, sige. Thanks guys for attending, and I'll see you next week. So I hope this one clarifies it, no? So ang carriers natin in the valence band are holes, carriers natin in the conduction band are electrons, no? The valence band is full of electrons, but they're all useless, essentially.
Thank you po, sir.
All right. Sige, bye-bye. Right, so if anyone has any more questions, please ask them in the Discord na lang kasi may meeting din ako, and I'll see you guys next time. Bye-bye.